Oh, by Friday?
Okay, thanks.
Okay, so you got another question? Any other questions?
You can pick them up upstairs, next to the place you dropped them off.
Okay. So last time we started talking about MOS-capacitor. And what we saw is that in the case that we started with a MOS-capacitor where we had an N-type semiconductor. So the structure we looked at is the MOS-capacitor. And we said, well, we have an N-type semiconductor, and we had a piece of insulator, usually silicon dioxide, and we said we had a conductor. We called it metal, but it's typically nowadays made out of highly built polysilicon. Anyway, it's a conductor. So it's a conductor, insulator, and semiconductor combination. Okay, and then what we saw is that, well, if we applied positive voltage to this gate, what we saw is that electrons accumulated at the surface. And the energy band diagram, that picture was relatively simple. So if you looked at the energy band diagram, we applied positive voltage, which appears as lowering the Fermi energy on the left-hand side. So this is basically EF metal. And then as a result, what happens, the Fermi energy level has to remain constant inside the semiconductor. But the bands won't have to bend because these chi's are constant, these electron affinities are fixed. And therefore, what we had was something like this. Oh, yeah. Except for the fact that I'm actually doing the opposite. So I have to apply positive potential here, right? So I'm lowering this, and this is an N-type semiconductor. So in the bulk, what we have is that you have a Fermi energy that's closer to the conduction band. And then when we bend it, it gets even closer to the conduction band and farther away from the EI, the intrinsic Fermi energy, which implies that we accumulate more electrons at the surface. Right? So that was the accumulation one. And then we saw if we applied the negative voltage, what that did was basically like pushing this up. It's equivalent to pushing this level up. And when we did that, the energy band diagram looked like this. So we had some electric field drop across the oxide. And then what we had is that beyond that, also we had a little bit of a band bending here. The band bent like that. And then this was your EI, which is almost in between EC and ED. I mean, it's not exactly in the middle, but it's very close to the middle. So this is EI. And this was EC and ED. But since there's no current flow in this case, inside the bulk, the EF, so we are in thermal equilibrium, and the EF remains constant across. So the Fermi energy remains constant, like let's say. So Fermi energy, short color actually here. So this was EF, this is EF, and you saw that actually EF and EI got closer to each other, which means that we have now, instead of accumulation of charge, we have depletion of charge. So we deplete the region of electrons, and what we're left with are these positively charged immobile ions, which form a depletion region here, and you can see them like that. And of course, the charge is balanced by a negative charge at the surface of the conductor on the other side. Right? And if you look at this picture, you will see that there will be some energy, some potential drop across this depletion region, and then some additional potential drop across the oxide. Right? Because there's electric field across the oxide, so there will be potential drop there. And then we also, in doing all of this discussion, we made two assumptions initially. The two assumptions that we'll have to come back to were, number one, that the work function of the metal and the work function of the semiconductor were the same. And we know that this assumption is almost never true. Unless some magical combination of numbers happen for these two materials to have the same work function. It doesn't happen. But we are making this assumption, we'll come back to it, right? So we'll have to have this assumption. Number two, the assumption we made is that there were no charge centers inside inside the oxide or at the surface. And that's not a true assumption either. So we'll come back to that too. But let's start with that. And when we had those assumptions, what happened is that when you applied the 0 voltage here, the band structure was flat. And therefore those assumptions are basically called flat band assumptions. So, now, this was the depletion. And then once we applied even a yet more negative voltage to the gate, what could happen is that instead of now, EI and EF would cross. And you would drop even larger voltage across the oxide. And what happens is that this becomes even more bent. Because this has to remain constant, right? This difference is the difference between the electron affinity of the semiconductor and the electron affinity of the oxide. So this height has to remain constant. So when you push this up, this has to be pulled up. This is pinned here. So this is what happens, and EI is also bent up. And what you get as a result is that if you push it harder, if you basically apply a more negative voltage here, instead of extending the depletion region, instead in thermal equilibrium and hence the steady state, what happens is that you accumulate holes at the surface. And we saw that these holes were generated thermally through the thermal generation inside the bulk, and therefore they were slow in formation. Now, why did I emphasize the fact that this is in thermal equilibrium? Because if it's not in thermal equilibrium, this picture doesn't even hold. There is no EF, there's no constant energy level. Fermi level is constant only in thermal equilibrium. Now, you have to make a very clear distinction between thermal equilibrium and steady state. You can be in steady state but not be in thermal equilibrium. But if you are in thermal equilibrium, I guarantee you're in steady state too, right? But thermal equilibrium means that there's no exchange of heat or energy. And in this case, there's no exchange of energy. If you leave it like that, there's no transfer of energy from one side to the other. Now, let me give you an example where you have steady state but you don't have thermal equilibrium. There are many examples, but one simple example from thermodynamics. So let's say you have a hot reservoir and a cold reservoir, and you have some thermally conductive material between them, right? So you have, for the purposes of this discussion, you have an infinite amount of energy here and there, and you have an infinite sink of energy. So there will be a constant flow of heat. So you look at it, you can say in steady state, the temperature at every point is such and such. But you're never at thermal equilibrium, right? Or, in an electrical term, if you have current flow, you can have constant DC current flow. If you have a current flow, you're not in steady state, you're not in thermal equilibrium, but you could be in steady state. So you have to make a very clear distinction. And Fermi energy, this Fermi distribution, is only for thermal equilibrium. So you have to realize that. So that's important. And that's why we saw different behavior when we hit this thing with different kind of frequencies or different kinds of waveforms. So we saw that if you look at this capacitor and you apply a very large, very high frequency signal, sinusoidal signal to it, instead of getting the inversion layer changing, you will see the depletion layer changing. And that's inconsistent with this picture as it should be, because that's not thermal equilibrium. Okay? But now, so if you wait long enough, this is what's going to happen and this is what's going to happen. Okay? Alright. Now, what we saw in this case is that you're actually at the surface, you've created a different kind of semiconductor. And this is called inversion. Because at the surface now you have an EI which is higher than EF, which implies that you have a larger number of holes than electrons. In other words, you have a p-type semiconductor, and that's the inversion. Now, we wanted to define, so what do you define as the onset of inversion? Well, if you just care about the ratio of the electrons and holes being greater than 1, right? You would define it when these two cross. So this is the point where inversion occurs, right? Technically speaking. But at this point, you have very few charge carriers to begin with, right? So this is not a very useful definition. So another definition, which is somewhat arbitrary, but is more common and more useful, is that to define the inversion, the onset of so-called strong inversion, at the point where you have the same number of the opposite type of carrier at the surface that you had original carriers in the bulk. In other words, if you have the same density of holes, in this case, at the surface, that you had electrons in the bulk, that would correspond to the that we define as the onset of the strong inversion. And for that to happen, we know that the number of electrons and holes are given by these two expressions we derived before, right? So you know N is Ni e2 Ef minus Ei over Kt, and P Ni e2 Ei minus Ef over Kt, right? So what we are saying is that I want this potential difference to be the same as that. So let's call this Pf. So I want this to be Pf. And at that point, what can I say about the surface potential? The potential at the surface, Ps. Let's remember, the bulk is at zero potential by definition. So we define this as the reference for the potential. So what is the potential here at the surface? The electric potential. It's going to be 2 phi. Actually, more accurately, it's minus 2 phi, but let's forget about the minus sign in this case because you have to apply negative voltage. But so the surface potential, Ps, at this onset of strong inversion has to be 2 phi, right? And what is Pf? What is this difference? Can I calculate that? If I tell you I have a room temperature, for instance, and I have a doping concentration of Mg, how do I calculate that? Well, think about it. If I'm at room temperature, if I'm in the normal range of operation, it means that all of these are, pretty much all of these are ionized. So the number of electrons I have is, to a very good approximation, almost equal to this. So N is equal to that. So Nd equal to N is Ni E2. Now, the difference between Ef and Ei, which is what? Which is Q Vf by definition over Kt, right? Vf is this difference. And of course, you have to apply Q because this is electric potential and that these are energies. So, well, of course, all I have to do is just solve for Vf, which basically gives me Kt over Q, natural log of Nd over Ni. That's my Vf. So my surface potential is twice that. Okay, fine. Now, what I'm trying to do here, what I will try to do in the next couple of minutes, is to derive an expression for the minimum voltage I need on this gate. I mean, in this case, it would be negative voltage, so it would be but it's the minimum absolute voltage I need on the gate to make sure to create this strong inversion, to get the onset of strong inversion, to just be the edge of that, at that threshold. So, no surprise, we'll call it threshold. But we want to find that the minimum voltage, in terms of absolute numbers, in this case, that creates this situation. So how do I do that? Well, how is it related to, if I seem to know my Vs, the surface potential, right? But is that enough to know? I need to know one more thing. Yeah, this voltage drop. I need to know this potential difference, delta Vx. Right? I need to know that, and if I know that, and the sum of these two gives me the minimum voltage that I need to apply to get this strong inversion at the surface. Okay, so how do I do that? Well, I know one thing. I know my Vg, and I'm writing things in terms of absolutes, because this is a p-type, so this is negative, but so I'm not going to worry about the signs. So the gate voltage is the sum of the delta Vx and the surface potential. Right? So what I need to do, what I will try to do in the next couple of equations, is to try to write the whole thing in terms of surface potential. So I want to see if I can write the whole thing, the Vg, in terms of surface potential. In other words, I want to see if I can write this term in terms of the surface potential. But keep in mind that this is the potential drop where? This term. In the semiconductor, right? Across the depletion region. And this is the potential drop across the oxide. And it's important to keep this in mind because your book is completely messed is calculated. So in the end, they end up assigning the potential drop associated with one with the other one because the equations look like the other one. Just keep that in mind. Just won't go through this. Let's do it right. Okay. Now, what is that? How can I calculate that? Well, I know one thing. I know that I have this charge density here. What is the charge density here? Well, what is my electric charge density in the depletion region? Per unit
Q divided by
Q times ND. Right? Right? The charge density. ND is the density of the dopants, right? And the charge in the depletion region is formed by the dopants, right? Because these are ionized dopants. So the charge density here, really rho, is QND. Okay? So I can apply Gauss's law, right? I know that there is no potential drop inside the semiconductor. That's why it's flat, because inside the conductor, I'm sorry, because of the Gauss's law. And I know one thing. I know the potential, the potential here, the electric field outside this depletion region is almost zero. So I can form a Gaussian surface with these two sides, one here, one there, and this is zero, or I can form it even here, and then say, well, this is XD. This is the width of the depletion region, and I want to calculate my electric potential at X from the surface. So what is that? Well, I can calculate my electric field. How do I calculate? What is my electric field here? What is my electric field at X? It's pointing this way, E, and I have to form a Gaussian surface, and it's basically, since the electric field on that side is zero, it's basically this total net charge divided by epsilon, and or in other words, it's the surface charge density associated with this region divided by epsilon. Right? So what is the surface charge density associated with this region? This is the volume density, right? I want to convert it to surface charge density. I have to multiply by this length. Okay, so let's do that. So that would be QND times X, I guess X minus XD, doesn't matter. Right? But it has to be, well, it's X minus XD, right? And that's the surface charge density. Then divided by epsilon silicon, that gives me the electric field at X. This is for X is between 0 and XD. Okay, so that's my electric field. So I can calculate a couple of things based on this. One thing I can calculate is my surface electric field here. At the borderline between the semiconductor and the oxide. What is that electric field? I just need to set X to 0. So Emax, the maximum electric field at the surface, is going to be Q and the XD divided by epsilon silicon. There's a minus sign because it's pointing to the left. That's the maximum electric field. Inside the semiconductor still, right? Now, the other thing I can do, I can calculate my electric potential at any point. If I know the electric field, I can calculate the electric potential, right? How do I do that? Well, by definition, the electric potential, V of X, is minus integral of, from the reference, so that's called XD the reference, because that's where the bulk begins, and I kept that zero potential, to X of P of X dx. So I have to integrate this quantity from XD to dx, and it basically integrates, so basically it's X minus XD, so it becomes X minus XD squared over 2. Evaluated at these two values, so basically it gives you the electric potential would be Q ND over 2 epsilon silicon X minus XD or XD minus X squared, doesn't matter. Right? Correct, yeah. Okay. So that's the electric potential at any point I can calculate. And therefore I can calculate at the surface. Right? Just need to set X to 0. When I set X to 0, so the surface potential, so that this is basically the absolute value. The absolute value would be QND XD squared over 2 epsilon silicon. Or, conversely, I can say that the depletion region, the width of the depletion region is given by 2. I'm going to drop that absolute value, okay? So you know I'm talking about absolute value. That's going to be the width of the depletion region. We can solve for x in terms of the surface potential. And that basically, and I can plug it in, I can even calculate the maximum electric field in that in terms of the surface potential. So E max is going to be, again, let's drop the minus signs and all that. So this QND and that QND both appear in the numerator under the square root. So I get 1 over epsilon silicon. It's actually, let's keep that outside. Square root of 2QND epsilon silicon ds. So that's my maximum electric field at the surface inside the semiconductor, right? Now, what do I need to calculate what I was trying to calculate is the electric potential drop across here. And I said there are no charges inside the oxide. So what does that mean? It means that my electric potential drop across the oxide is simply the electric field times the width of the oxide, the thickness of the oxide, right? If there are no additional electric charges, it's constant electric field across. So the electric potential drop, delta Vx, is simply so the potential drop across the oxide is going to be what? It's going to be the electric field, Tox, times Eox, the electric field inside the oxide. But, is it the same as Emax, the maximum electric field here that I calculated? So let's call this Emax silicon. Is it the same? So I'm talking about the electric field inside the semiconductor at the surface, right? On the semiconductor side and on the oxide side. Are they the same? No. What is continuous? When you look at electromagnetics, right? At the Maxwell equation. What is continuous? What remains the same on both sides of a change in the dielectric constant? Potential remains constant, yeah, true, if you don't have charge surface charge. But there's something else. I mean, does the electric, it's one of the fields, but it's not the electric, it's not E. It's the D, it's the displacement. The normal component of D and the tangential component of E remain constant. And the way to see it is basically by looking at the Maxwell equations, right? Because, what you're talking about comes from this. And if you don't have any charge densities, it's 0. Right? Otherwise, it's just rho. So what it tells you that if you form a surface, Gaussian surface, so this with one side of the surface on one side and the other side on the other side of the boundary, then this integral has to be the same as that integral. So the normal component of D remains constant. In other words, what it tells you is that epsilon silicon times, so I know epsilon silicon times E silicon is the same as epsilon oxide E oxide. In other words, D silicon normal component is the same as D oxide. Right? I'm assuming isotropic material, all those things. I don't have any fancy tensor relationship. So, that's true, right? So the continuity is for the electric displacement vector. And this gives me basically what I need. It tells me if I want to calculate my Eox, I need to do, and this is basically E silicon max that I've calculated, right? So it's going to be E silicon, epsilon silicon, E silicon divided by epsilon oxide. Okay. And I already have calculated epsilon silicon, E silicon, right? It's that square root. So simply I can rewrite it as square root of 2, that's why I kept that epsilon out. Yes, divided by epsilon oxide. And what I'm really interested in, which is the potential drop across the silicon dioxide itself, is going to be Tox times that, so I get write it as Tox times epsilon, divided by epsilon ox, times square root of 2q ND epsilon silicon times square root of Vs. I just write it two different terms. Now, what is this term? COX is the oxide per unit, capacitance of the oxide itself, right, per unit area. So I can write this as 1 over COX. So I can write the whole thing as square root of 2q ND epsilon silicon divided by COX, where COX is epsilon ox divided by TOX, which is the surface capacitance per unit area. Okay, so that's delta phi out. And by the way, we give this quantity times square root of Vs. Now, this quantity we call gamma. This has nothing to do with the emitter injection efficiency. So in the context of MOSFET, it means a completely different thing. Just lack of creativity, I guess, or something like that. Alpha, beta, gamma, always. There's a lot of other Greek alpha. But anyway, so we can write that gamma square root of Vs. And gamma, by definition, is square root of 2q ND epsilon silicon divided by COX. Okay, so I did what I wanted to do. I calculated the oxides, the potential drop across the oxide in terms of the surface potential, right? So now, what I'm really trying to calculate is a threshold voltage, right? Minimum voltage, well, let's say, well, the first thing is Vg in terms of that, which was delta V ox, the voltage drop across the oxide, plus the surface potential, which now I can write as gamma square root of Vs plus Vs. And now, to calculate the minimum threshold voltage, where I have strong inversion, what do I need? I need to set Vs to what value? Vs needs to be what? The surface potential needs to be what? To have strong inversion, by definition, the way we define it. To have the same number of, in this case, hole as the surface as we have electrons in the bulk. 2Vf, right? So, therefore, the Vt0 prime, and I'll tell you why I'm using prime, because I haven't adjusted for my simplifying assumptions, the flat band assumption yet, is, well, I'm going to write it like this, 2Vf plus, I'm going to change the order of this, gamma 2Vf. Now, you see that all of the constants associated with many of the constants associated with the bulk, with the bulk of the semiconductor, appear in gamma, right? But this should not, and actually this looks very much like a depletion capacitance. So one-sided depletion capacitance, if you look at the expression. So effectively, gamma is a dimensionless quantity, unitless quantity. Well, it's not unitless quantity, actually it has 1 over square root of, it's square root of bulk, but it's a quantity that's like a ratio of 2 capacitors. The depletion capacitance, which is the one that you see underneath, and the oxide capacitance, which you see on the top. And you'll see what the significance of that is later on. But although that's the case, and this very much looks like a potential drop, across a depletion region, right? Because it has the square root and all that stuff. This is the potential drop across the oxide. And this is the potential drop across the depletion region. Alright? So, but I have an expression, and I know what Vf is. I've already calculated Vf. I have an expression for the threshold voltage, kind of. Right? Because still I have those two simplifying assumptions that I started with. Now let's go back to those assumptions and see how we can deal with them. Actually, it turns out it's very easy to deal with them. Now, one of the assumptions was that the work function of the metal and semiconductor are the same. Right? Which is not necessarily true. So now if they are not the same, what happens? If they are not the same, you can calculate the difference between them in terms of voltage. So it's basically Q Vm minus Vs. And if you apply this voltage to them, if you apply this voltage to the gate, that brings you to the flat band condition. So this is the amount of extra voltage you need to apply to the gate to induce the flat band condition. So instead of that happening, the flat band condition happening at 0 gate voltage, it will happen at this voltage. So this will have to be added to my threshold voltage to give me the real threshold voltage to adjust for the difference in the work function of the metal and the semiconductor. Now, I also said that there are other terms, right? There are other there could be charges at different places. Now, one of the predominant places where you can have electric charge, constant charge, is at the surface of the oxide and the semiconductor. So if you look at this surface, this boundary, right? On one side you have these silicon atoms, right? So you have mostly silicon atoms on the semiconductor side. So you have these silicon atoms, right? They have 4 covalent bonds, right? Each one of them. 3 of them are happily bonded to other silicon atoms on the bottom side and the side, right? But the 4th ones are going into something which is different, which is the silicon dioxide that has a different structure and all those things. So there are these dangling bonds here, which can actually attract a lot of a second electron, trap a second electron, and form a charge center at the surface. So you have this layer of constant electric charge which is not mobile at the surface. And that creates an additional voltage drop. You need to have an additional voltage. How much? Well, this is at the surface, right? So it's like a parallel plate capacitor. So it's this charge divided by this capacitance. Q is CV. The voltage you need to compensate for those is simply the surface charge divided by Cox. And it's a negative charge, so it's usually shown with that. So surface state's charge divided by Cox, that gives you the voltage that you need, the additional voltage you need to adjust, to apply, to compensate for it. Now, so let's look at all of these terms so far. So I have EMS, and so the threshold voltage, VT0, is that. Then there's and of course I have my standard threshold voltage, so VT0. So these are the correction terms. Now, you can see from this that in general, you are at the material's constant's mercy. So if you do it just like this, if you make a MOS-capacitor, your threshold voltage will come out to some value, some number. Maybe negative, maybe positive, maybe very small, maybe very large. Depends on what kind of materials you use. So you have no control over it. But as a designer, you would like to be able to control your threshold voltage to a value that makes your design, circuit design, as we'll see later on, straightforward and effective, right? So I need another term that I can control to basically compensate for all of these variations. So there are all these things that push it in different directions. And in the end, I can come in, and if I could come in and adjust it somehow, I have this final knob I can turn and bring the value of the threshold voltage to the value I need. I should be okay, right? Now, that's called an implant charge. And when we'll talk about, when we'll see that tape on the fabrication, you will see how that works. But basically the idea is that you actually introduce additional ions through ion implantation. So you accelerate ions and put them inside the channel, inside, right under the oxide. You implant additional charge at the surface to just enough charges to compensate it by the right amount. And that Q implant is also, did I use lowercase I? Yeah, keep it consistent, let's keep it lowercase I. And so that's the final term that is what I control, probably the only thing I control in this equation, that I just implant enough charges there to get this voltage to what I want it to be. So now, in the end, this is my threshold voltage. Now, all of these terms, so this takes care of this takes care of the second assumption. So I've taken care of the two simplifying assumptions that I made early on. Now, the whole thing is usually called the flat band voltage. So you lump all of these other additional correction terms into one term, and therefore your VT naught, the threshold voltage, would be flat band voltage plus 2 phi plus gamma square root of 2 phi. And this is your threshold voltage. This is the minimum voltage on the gate that you need to induce inversion charge, strong inversion at the surface. It doesn't mean that below this voltage you don't have any inversion charge, right? We know we do. And that's cause for sub-threshold current in MOSFETs. We'll talk about it a little bit later. But other than that, that's what I need to induce that kind of strong inversion at the surface. Now, I've done all of this to calculate this quantity, VT naught, right? But what I really care about, if I want to make a transistor transistor out of this is the charge density, the inversion charge density at the surface, right? So how do I calculate that? Well, you know, I say, so I'm going to make an assumption, so keep this in mind. This is a simplifying assumption, it's not like any other simplifying assumption, it's not technically correct, it's an approximation. Well, think about it. I say, well, I ignore all the charge I've induced at the surface, all the inversion charge, up to this point. Because that was not large, I mean, it's a weak amount of charge. But anything beyond this point, if I apply some voltage in addition, in excess of this voltage, then that could induce a lot of charge. Because now I am already at PF, so any change will increase my EI, raise my EI over EF by a larger amount, and through the exponential I get a much larger number of charges, which is proportional to the potential applied to the gains, right? So, what can I say about the surface charge density? Beyond this, I simply have a capacitor, right? So if I ignore all the charge I've accumulated up to this point, which is not large, then I say beyond that I have a parallel plate capacitance. So what is the inversion charge, the strong inversion charge I will induce on the surface if my Vg were above Vt naught? So I say the Q inversion, and we understand this is the strong inversion, per unit area is Cox, it's a capacitance, right? Except for the fact that it has a certain offset voltage, it has a certain threshold voltage that needs to be met first before you get the extra voltage to induce additional charge. So it's Vg minus Vt naught. Does that make sense? So I'm saying that any voltage in excess of Vt naught will induce additional charges, which is basically a capacitance charge. It's a QCV. So this is a very important expression. It's very simple right now the way it is because I've lumped everything into this Vt naught. Okay? And we'll see why we use the knots here, because when we go to the MOSFET, the actual transistor, then you'll see that how it can change through the substrate voltage, basically. Okay, any questions up here? No. Alright, good. So that's the basics, those are the basics of the MOS-capacitor. So now let's start talking about the MOSFET. So far we've made a capacitor, we could induce charge. We could control the channel charge, the inversion charge through the gate terminal. Now, if I were to make a transistor out of it, a transresistor out of it, right? If I wanted to change the resistance of something, how could I do that? Well, I need to add two terminals, right? Between the two sides of this capacitor and flow current laterally. I could do that. So what I could do is I have my oxide, so let's show that. So this is the insulator, and then I have a conductor, which is the gate. Now, in addition to these, so I can form a MOS-capacitor here, right? And then for this discussion also, let's assume that this is a p-type. I'll change the type, so we've dealt with both times. Now, what I need to do, I need to create two contacts. If I could somehow make a connection to this side and that side, I know, in this case, when I apply a positive voltage here, at some point I invert the surface and I will have electrons here, and these electrons can carry charge for me. So I need to make some contact here. Now, can I make a p-type contact? So if I were to make these contacts, let's say here, can I make a p and p, or maybe higher doping level, let's say, to make it low resistance? Can I make it like that? If I make it like that, what happens? Can I turn this transistor off? Or this resistor, can I make this resistor very large? Basically, can I turn the connection between these two off? No, because I have P, three different kinds of P's, right? There's no way to turn it off. I want something that's normally off. Okay, so if I'm using a p-type substrate, I have to use N plus contacts, and vice versa. So now, instead of this, what I need are two regions, N plus. Now, when I do something like this, what have I done? Without the gate, without applying anything to any voltage to the gate, what do I have? I have an NPN structure. So I have two back-to-back diodes. we'll see it in the circuit design, you have to really treat it as a 4-terminal device. In fact, MOSFET consists of 2 transistors. Basically, it's not a single transistor, there are 2 transistors. You will even see that in the model. There's a MOSFET and there's a JFET. But we'll see. Okay, now, so let's set one of these as a reference. So let's call this the reference source for the reason that will be known. And let's say, in general, the most general terms, there will be some voltage here with reference to the source. So we call this VDS. Let's call this drain. And this is the gate, so we can apply some voltage to the gate with reference to the source, so VGS. And in general, we could apply some voltage to the bulk, so, and let's call this is the bulk terminal, VSB. Okay, so there are 4 terminals here. Now, let me ask you a question. If I apply a positive voltage to this, let's look at the energy band diagram for the P-type bulk quickly and see how it behaves, right? So one of the things is that I know it's a P-type semiconductor. So is EF above or below EI? Below, right? So if this is EI, this is EF originally. Now I am putting it at so let's put it next to the oxide, and let's say under flat band condition it kind of looks like that. Now, if I apply a positive voltage here to the gate, what do? I basically pull this down, right? These are all potentials for electrons, which are negatively charged. So I pull this down. If I apply positive voltage, this goes down. If this goes down, let's see what happens. So this energy band starts bending. This one starts bending, and this one starts bending, and then I have some additional potential drop across the oxide. And my EF, in thermal equilibrium, looks like that. So that's how I invert that surface. But now you can see, in this inversion, I have a case where EF is above EI, therefore at the surface I have an N-type semiconductor. Just the opposite of the other one. This shouldn't be that surprising. Okay. And this is basically where the EFM, the metal EFS. So this is the potential drop across. This is due to the potential drop across. So this is for a basic P-type MOS capacitor. But now, there's one fundamental difference between this structure that I've shown here and the MOS capacitor. In the case of a MOS capacitor, we saw that this inversion charge was formed through thermal generation, right? And therefore it was very slow in formation. It had to be dissipated through thermal recombination, right? Now, is anything different here? What kind of inversion charge will I have, by the way, when I apply the positive voltage here for a P-type substrate? The inversion charge is electronic, right? It's made out of electrons. So I'm forming a layer of electrons at the surface when I form the inversion layer. And that's in addition to the depletion region I have here, which has kind of these negatively charged ions. So there will be a depletion region around it, but in addition to that, there will be a electronic charge at the surface. Now, where would those electrons come from? Do they have to be thermally generated this time? I mean, of course, a few of them are generated thermally anyway. But now I have a source of electrons right next door. I have these huge sources of electrons, the way I've designed this device. Therefore, I can generate these electrons and dissipate them very quickly, unlike the MOS capacitor. So, although the MOS capacitor was very slow in responding, creating this conversion layer charge, this device, because of this abundant nature of abundant electrons available in these source and drain PN junctions, can be turned on and turned off very quickly. So you see the limitations for that when we went to kilohertz. So once, for a MOS capacitor, once we went above kilohertz or tens of kilohertz, it just did not react fast enough. But now this time, since I have these sources, it can react very fast, and you have MOSFETs that operate up to tens of gigahertz, hundreds of gigahertz nowadays, right? That's the reason, because you have a source of electrons right next door. So when you apply this voltage, most of the electrons are really coming from these guys. Now, when you see that, you see even on this surface, in the simplified picture, you have basically a channel formed by N-type. So it's N plus, N, N plus. So you can carry current. Now, this current flow, due to the electric field, if you apply a small electric field here, there will be current flowing, right? This current flow is basically a drift current flow, right? Because at the surface, these electrons are majority or minority carriers. They're majority because you've changed the surface to N-type. You've inverted the surface. So they are majority. There's plenty of electrons available. So they're moving randomly, thermally, and every so often, basically, they're bounced off. And what happens is that when you apply the electric field, it shifts the mass. This electronic cloud from one side to the other. Now, if I apply positive voltage, where would the electrons start and where would they end? If I have a positive voltage here, small positive voltage, let's say for now, the current will flow in this direction, right? Which means the electrons are flowing from this direction, from left to right. Now, hence the name source and drain. So they're the source and the drain for the charge carriers. So to tell which one is the source, which one is the drain, you have to think about what kind of charge carriers you have. So in the NMOS, you have electrons. So electrons start from here and end there, so source and drain. And this is what gates them, controls. This is the gate voltage, and this is the volt. Okay. So that's a very simplified picture. Now, from an energy band diagram picture, also you can look at this. Now, I can draw the energy band diagram in this direction. Remember, that energy band diagram is in what direction? It's along this axis, right? That energy band diagram. Starting from the metal, well, the conductor, oxide, insulator, and semiconductor, right? Now, I'm going to draw the energy band diagram along this axis. And you can see, unlike the bipolar transistor, whose behavior could be predicted through a two-dimensional model, what we had was really a two-dimensional model, right? We didn't think about, because we said, well, all assume uniform current density across this kind of rectangular design. But now here, I can't predict the behavior of this device with a two-dimensional model. I have to really think about it three-dimensional. So there's an extra dimension. Now, so I can look at the energy band diagram along this axis, and let's do that right here. So before I apply the gate voltage, so let's say below the threshold voltage. This is the way energy band diagram looks like. So this is EF. I have N-type here on this side. I have P-type, and this is N-type. So if you look at PI, it kind of looks like that. So I have P-type material, N-type, and B-type, which will be consistent with this picture we had before it was bent. So this is this picture looked at in this direction. So I'm taking a cross section here, looking at it normal to the whiteboard. It's that picture. Okay? Now, when I apply a positive voltage to the gate, I can use this condition. So I start pushing the energy band down in the middle. Right? That's what I'm doing here. I'm putting it down. So what happens, I gradually lower it and lower it. And at the onset of strong inversion, what I've done really, I've created a situation like this. Where EI remains under EF at all times. So I have one type of semiconductor all across. It's all N-type. And that corresponds to this picture. Well, this is a little more important than that. Right? Does that make sense? Now, if I apply a little electric field, it means that I'm basically pushing this side. If I apply positive voltage here, it means that I'm pushing this down. So now, instead of this being flat, you can be in a situation where this is a tilt. There's a little slant to this energy band diagram. Now, what happens? I have plenty of electrons. I have tons of electrons here. Right? This energy band, there are electrons. It's not a huge barrier. It's a very small barrier, in fact. So they could move freely before. I mean, even before I applied this. I mean, a lot of them moved from left to right, and the same average number moved from right to left. So there was then no net current. But now, when I apply this electric field, there will be a few more moving from left to right than the ones that move from right to left. So I can have a net current flow from drain to source because they're negatively charged. So my net current flow would be in this direction, while the electrons are moving from left to right. Okay? So I'm lowering this potential, and I can even calculate what this current is. So well, we know this is a three-dimensional device. So let's look at it as a three-dimensional device. So let's say this has a depth. Let's look at the depth of these things. So these junctions have a certain depth, and the so let's look at the perspective. And that. And so let's say this length, this channel length, right? We call this L for channel length. And let's call this dimension the width of the device, W. We'll be dealing with the W and L's a lot when we get to circuit design. So keep that in mind. Now, we got the W and L in this device, and I want to calculate, let's say, what is the current flow in terms of VGS and VDS. Let's say VDS is 0 for now. VSD is 0 for now. Very simplified picture. How do I calculate the current flow? Well, let's see what is my charge. My child charge, Q, the inversion charge, right? What is the inversion charge in the channel? Assuming that the threshold is some VT or VT0, let's say VT, right? So the inversion charge is not per area, the total net charge in coulombs, is the charge density, which is basically VGS minus VT, right, times the area of the channel, right? What is the area of the channel? W times L. Now, how long does it take for electrons to go from here to there on the average? Well, what kind of transfer mechanism do I have? It's a drift, right? I'm applying electric field. Let's say VDS is small, so I'm talking about small VDS. Small VDS. Now, if VDS is small, there will be electrons moving from here to there through drift. So what I know about the drift velocity, I know VD is what? Is proportional to the electric field, mu E. And if the voltage is small, I can just assume that the electric field is almost constant across this channel, right? The lateral electric field. And if that's the case, what can I say about time it takes? What can I say about the electric field in terms of VDS? Sorry. First. So, if the electric field is constant across this, is it fair to say E times L is VDS? Right? The voltage drop across here is E times L. Otherwise, it would be the integral of EDL. I assume it's constant, so it becomes E times L. So this becomes VDS over L. And this is mu n because there are electrons. Now, that's the velocity. If I want to calculate the time it takes, the average time for an electron to get from the source to the drain, what would that be? Well, it's the length divided by velocity, right? So it's L divided by VD, which gives me L squared over mu n VDS. So this is the average charge for small VDS. This is the average time. What is the current? ID is the ratio of that, the average current. Under these conditions, a simplified assumption. So it's this guy divided by that guy. One of the L's from here cancel that one. You get mu n C ox W over L VGS minus VT times VDS for small VDS. What does that look like? What can I say about the relationship between the voltage between these two terminals and the current flowing through these terminals? It's linear, first of all, for small VDS. So it's like a resistor, right? But it's a resistor whose value is controlled by the voltage across the third terminal, VGS, this voltage. So it's a variable resistor. I can change the resistance by controlling VGS. And therefore it's a transistor. Okay. So it's a very simplified picture, of course. This is, and we'll derive more accurate expressions in a few minutes. But this is the essence of the MOSFET. There are a lot of, so this is the zeroth order effect, or the first order effect. This is the first order effect. We'll talk about a lot of second order effects in a few minutes, and we'll see that there's a more accurate expression that's nonlinear. It captures that, and then we'll see what happens when we apply larger voltages and all this. But this is what captures the essence of it. It's a drift device. What you've done, you've created an N-type region, albeit with different numbers of electrons at different points, but nonetheless they always have electrons as majority carriers. They never become minority carriers. They're always a majority, and therefore there's plenty of them, and therefore what you do when you apply an electric field, you create a net flow in one direction or another due to the drift on top of this very large thermal movements of the electrons that you already have. Okay? Now, there's one thing before we go forward that I need to talk about, and that's basically what this threshold voltage is. So I said this is the immersion chart, but now I have to take one more thing into account. The fact that I have this fourth terminal. Think about it. If this voltage were not zero, the voltage between source and bulk, this VSV, were non-zero, what would it do to my device? What would it change? Look at the transistor and tell me, what will it do? Would it affect my threshold voltage at all? Do you expect it to affect the threshold voltage? Well, okay, fine. Yeah, it does. Which part of the threshold voltage it would affect? Well, it wouldn't affect the flat band voltage because those are kind of coming from the fundamental properties of the materials and the surface charge density and the implant charge and all those things. So those are not affected, right? Which one of those two remaining terms would be affected? The surface, this one, or this one? Tell me, what was this term? This was the surface potential necessary to have a strong inversion, right? This was the minimum necessary surface potential to have strong inversion. And what was this one? This was the voltage drop across or the potential drop across the oxide. So now, if I change this, what I do, I'm changing this with respect to this terminal, right? And hence that terminal, because that's also reference to this one. So there is a depletion region right underneath this. First we have to form a depletion region, and then we have to get the inversion rate, right? Now, it would make, let's say this is a positive voltage, so it makes the depletion region larger. It extends the width of the depletion region, right? Now, which one of these two terms do you think it will affect? This one or that one? The surface potential, the first one or the second one? This term or that one? The second one. Why? That's the correct answer. It affects the second one. Why? Well, the capacitance is constant, right? These terms are not affected by that. None of these, right? But think about it. When I apply this voltage, I'm extending my depletion region. So I have basically a larger charge here. Okay? So effectively, the electric field here at the surface is larger, and hence the electric voltage drop, electric field across the oxide is larger, and therefore that term should be affected. You say, why isn't this term affected? Because it seems that everything is happening here, and this term was associated with the potential drop across the depletion region anyway, right? But remember, this is the condition, no matter what kind of electric field I have, the condition for having a strong inversion is having the potential here, which is 2F, 2Vf, with respect to the that drop will appear in this term. How does it appear? It just adjusts this voltage, right, by VSP. So basically, now this term has to be modified. So the actual VT is VFB plus 2Vf plus gamma 2Vf minus VSB. So now that's the way it's modified. And, well, we usually don't want to deal with all of these terms when you're designing circuits, so we rewrite that in a slightly different way. We say, well, VT is VT0, the original VT0 that we have, plus gamma times square root of 2Vf minus VSB, actually, well, plus VSB, because of the polarity. The way of defining it minus VPS. Just minus square root of 2Vf. Remember, there's a gamma square root of 2Vf in the VT naught, right? So this term cancels that, and what is left is this term. So this is exactly equivalent to that. But the good thing is that all I need to tell you from now on, if I'm a circuit designer, is gamma, 2Vf, and VT naught. Right? I don't need to tell you what is the work function of the metal, what is the work function of the semiconductor, all those things. All of those are absorbed. What is the density of the implant charge, blah, blah, blah. All of them are absorbed into VT naught. Now, this is called the body effect. See, the body can affect the threshold voltage. And through that, basically, it can affect system. If you keep the threshold, this voltage, the gate voltage constant, by changing this voltage, you can actually change the threshold voltage and hence change the resistance too. Right? Because if I keep this voltage constant and change the other one, still it results in a change in the charge, and therefore it results in a change in the resistance. So I can modify this or that. And that's why I said I really have two transistors in a MOSFET. I have the original the surface FET MOSFET, and then I have the backgate JFET. Behaves like a JFET. Because they're in parallel. They share the same drain and source. But there are two transistors involved. And that should be, actually that is also consistent with this picture. You see, the ratio of the strengths of these two transistors is the ratio of the strengths of this capacitor, the depletion capacitance, to the oxide capacitance. Which shouldn't be that surprising either. Because these are capacitively coupled devices, right? These are field control devices, field effect transistors, right? So the stronger capacitor gives you stronger coupling to the channel and better, more control. And we'll see that, we'll talk about this more and more. We'll see it in different ways. Okay, let's take a quick break here. And when we come back, what we'll do, we'll go and analyze this transistor from a kind of a more accurate. So we'll go through an analysis that allows us to derive the more general nonlinear expression for the transistor. Okay, any questions? All right, well,